Welcome to Xiphera's Cryptography Under the Hood webinar. In today, we are going to look what digital resiliency is and how it can be established. I am Valtteri and I will be your host in today's webinar. Before diving in, let me first introduce our company for those who haven't met us before. So Xiphera is a Finnish company founded in 2017. We design hardware-based security solutions using standardized cryptographic algorithms, and we offer implementations as intellectual property cores, or as we say, IP cores. Our product offering includes cryptographic algorithms and protocols, and those can be easily integrated into FPGA, ASIC, and SoC designs. For more information, please browse our websites at xiphera.com. And just a couple of practicalities about this webinar. Please send any questions at any time using the Zoom's Q&A inbox found in the Zoom app. And for the information, this webinar is being recorded and it will be accessible later with all the material along with the previous webinar at our website. And now we can move to our actual agenda. So let me introduce for today's speaker, Petri Ehkonen. Petri has over 30 years of experience in various technology industries. His experience covers engineering, project management, and marketing and sales positions. Petri holds master's degree in electrical engineering at Aalto University and bachelor's degree in social services and healthcare. The stage is yours, Petri.
Thank you, Valtteri. So today we will be talking about fortifying digital resilience, and we are looking also what are the security foundations for IoT, AI, and cloud systems. This is a wide topic where I try to put also the cryptography on this context. So the overall agenda is divided roughly on 4 sections. So I will first review this current industrial landscape and also looking for what is the role of the business pressure for the security perspective. Then what are the security elements, how to grow digital resilience, and what if we talk about system of systems. Finally, I'll be reviewing some example solutions which increase the digital resilience. Naturally, those solutions are based on modern cryptography on hardware, which is our specialty. Looking for the industrial landscape, we have some megatrends that dominate on this scheme. So digitalization continues and connectivity increases. What this means that there are more devices that are digitalized, like thermometers, pressure meters, refrigerators, washing machines, you just name it. And so all of those devices seem to be more and more connected to the network, so they are sharing information. At the same time, the complexity of these platforms where they operate and these computing systems is growing. So it's not anymore like one system design, but it's typically system of systems design. What we also see is the platforms and data domains, they diffuse. As an example from that is that everybody knows 3G, 4G on the mobile networks. We have now 5G and 6G is coming. Those are based on the 3GPP release 17, 18, 19, and going forward different specification numbers. And when we look in the past and the present, maybe those platforms operate on the ground. But in the future, those specifications also occupy space. So these same platforms and data domains are deployed on the satellites. Also, this value of the AI models and AI data is increasing. We see increased number of the AI solutions deployed. And unfortunately, the last megatrend I have been highlighting here is that the security environment has been showing increase on advanced attacks and data breaches quite recently. Namely, these advanced attacks are lateral attacks. When they find one entry point, they penetrate the whole system. And the data breaches, unfortunately, are coming from the vulnerabilities that have been known, or maybe sometimes zero-day vulnerabilities. Now, when we combine this industrial landscape from the fact that this IoT, cloud, and AI solutions, the number of those solutions is growing exponential. Also, the users are, of course, then growing, and the business demands scalability of these services. Then, looking for these systems or security of systems of the decentralized services, it's quite hard to guarantee the security from the device, IoT device, to the cloud service to the end user. Unfortunately, I didn't put it on the megatrend, but when we are talking with the industries, quite widely on the industries, sometimes and quite many times on the non-critical infrastructures, the security seems to be on the secondary position on the system designs. Well, that leads on the conclusion that this demand to match the market needs leaves equally high pressure for fast development cycle of services. So if we have high number of services and they're developed faster, that is actually increasing the risk that we don't have any more digital resilience if the underlying infrastructure is not thoroughly secured. If we are looking for what forms digital resilience and what are security elements, so these modern computing platforms and computing solutions have a lot of interdependencies if we are looking just the service itself. And those are quite complex to map. If you're looking for the picture on the left-hand side, which is originated from Digital Europe, they are expanding actually these security elements more than just components of the system, but it's coming from the skills, supply chains, vulnerabilities, hybrid threats. So we need to have built digital trust for system of systems on the several levels. So if we require defense in depth in systems, that leads to requirement to have digital resilience. And if we want to have digital resilience, that requires that we have digital trust. That trust originates from the supply chain, from development tools, development software, manufacturing chain. We also, that trust is that we are using the best fit elements and algorithms for the solution. And trust of these individual computing elements, we have to be able to guarantee the authenticity and integrity of the service, and authenticity and integrity of the system itself. Now comes, of course, the question that, is the digital trust alone sufficient requirement to guarantee the digital resilience? How about the system configurations? One system, one domain is configured differently than others. Also, the access controls are different. Can we guarantee the security and confidentiality of AI models that we deploy on the cloud, or the edge, or the device itself, and the data coming out from there? So we believe that selecting the correct security elements requires customizable solutions, that we customize it for the need. Equally important is to have agility to respond changing security requirements on the several levels. This is now just one view of the components of the digital trust to build the digital resilience. when we're looking for the resilience on system of systems, the IoT or industrial IoT, cloud and AI services, they are examples of the solutions operating as system of systems. When analyzing that, different threat models and so on, the supply chain is the basis of the trust. So I repeated that, I said it in the previous slide already. So that means that software compilers and libraries need to be trusted. So it means that we have to check those not to have any vulnerabilities or malicious functionalities. Digital designs, and now I mean hardware, digital hardware, and the design tools and synthesis results need to be trusted. So it means that those designs should be reviewed against any vulnerabilities or malicious functions. Electronic components, such as memory, CPUs, power supply components, radio frequency components, just named a few. That manufacturing chain of these components has to be trusted, so we should have access to manufacturing audit trail. And then when we have all these components, I mean physical components and software, pieces of software available, then whoever is manufacturing the device itself that is deployed somewhere, it has to be somehow trusted. So we need to be sure that no malicious operator can put additional software there to weaken the system or make backdoors there. So we need to have some access to the audit trails. So the claim is that foundations of digital resilience is built on validated system components. And even if we have secure components A and B, those secure components have to be used securely. It's well known that if we have secure components used in unsecure way, it eliminates all the benefits of using the secure components on the first place. So I roughly go through some example solutions that we have for the secured boot, hardware root of trust, confidential computing, and secured AI. So now if I'm looking for device itself, so we have to be able to verify that the system is powering up properly. So the operation of the device when you power it up, it doesn't matter if it's battery powered or if it's a power supply source power supply. So these motherboard configurations, if there's a motherboard, they are stored on the non-volatile memory, and those are used by the BIOS or UEFI. And if it's an embedded device, it might not have the configurations. But on the next stage, quite after that, when the platform is powered up, the system is performing boot image loading. So it powers up somewhere and loads the code of the operating system and drivers for the system. And for that one, we should be able to validate the boot image. So quite often it's coming now more and more popular and more understood that this boot image should be digitally signed for authenticity and integrity. And if it's kind of complex system, it might be that the boot sequence have several boot blocks where some of these have to be also encrypted with authentication, so authenticated encryption. So to increase the digital resilience for power up sequence, we need to have ability to calculate digital digest with the hash functions or cryptographic hash functions. We need to be able to generate keys for symmetric and asymmetric algorithms. Digital signatures should be provided with the classical and post-quantum cryptography algorithms. And when these signatures are created, of course, we should have then tool or service that is trusted that we can generate these signatures. And finally, of course, this complete chain has to be supported by the CPU, any device that is powered up, so that the semiconductor device should be able to perform the verification against this boot image, these signatures. So now we are on the point we have the system powered up and the operating system is running. Unfortunately, it seems unavoidable that there's some vulnerabilities will be still present. Even if we have the secure supply chain, those vulnerabilities can originate of the design itself that has been made some mistakes on the way, just figured out something afterwards. Also, secure boot cannot protect against the vulnerabilities originating from CPU, operating system, or support libraries that are used by the applications operating on top of that. So the hardware platform should offer solid root of trust, and we say that it should be hardware root of trust. Some of those, quite generally, the trust is now offered by the trusted platform models, TPMs, or subset of those. And there exists open source root of trust like OpenTitan and Calyptra, but they have induced inside, they have a CPU. So it means that there's some part of the operation is running on the software. So we believe that hardware root of trust should be provided with state machines. So the services that are needed is that we should be able to authenticate, encrypt, and decrypt software that is delivered for the platform. Ability to manage the digital identities and generate those needed. Key generation for the cryptographic primitives and algorithms and the management of those, naturally including ephemeral keys. And the secure boot that I said earlier is also part of this hardware root of trust, is inherently inside of them. As now the systems are getting more complex, this hardware root of trust should be easy to validate and certify. So for that reason, we believe that the system should be on state machine based. Now we are in a good situation if we have been building the trust so far and that we are resilient, that we are looking how to deploy applications on this environment. So for that one, we need to have something that offers confidential computing enclaves, and that is typically an engine that we can provide. So when the secure boot and hardware root of trust are used earlier, those are used on the same platform in the way that whatever application is then deployed to this trusted execution environment or enclave is properly protected from the source to entering on this enclave. Unfortunately, existing confidential computing enclaves like Intel SGX and ARM Trust Zone, they have several vulnerabilities both on the hardware and software. So these problems with these trusted execution environments on the Intel and ARM, they originate on these predictive branching or cache flushing problems. For example, there are other problems also. And that combined with the need that they are running different applications on the processes that are not isolating the information properly, that is actually one other reason for the vulnerabilities on the trusted execution environments. So we have been looking at this quite differently in the way that we have been creating confidential computing engines that are customizable for the purpose that is needed. And those offer complete isolation and protection for both of the code and data from the rest of the system. What it means that we could have several enclaves inside, and there's no physical access to the data and code from enclave to the other enclave. And to achieve that, we are using also our special IP core, what we call crypto module, that we are tailoring for the purposes that is needed by the computing engine. Finally, now when we have this, we have been powering up the system in a secure way. We have been able to deploy our AI model with the confidential computing engine itself. That is actually when we say that we can secure AI and AI model So it should be, and it is, protecting the data and code, the AI model or machine learning model. So we have dependency, or we have the trust chain, so that the development elements, the development tools and elements that we use, we trust those. Individual components, we are trusting those. Computing platform is also trusted and secured. AI model deployment is secured. For example, now we could be using for deployment TLS 1.3, for example, encrypting from end to end, so that there's no plain text available on the system, on the cache, or the drivers anywhere. So this electrophysical isolation of the AI model and data, I think we believe is quite unique. Now putting it all together. So the foundations for the digital resilience coming from originate from the need for the digital trust and also for supply chain trust. So what I shortly describe is how we securely boot system up, how we provide hardware root of trust to be able to deploy applications on the system, and finally, how we can have isolated computing enclave, computing engines that can operate AI or machine learning models, or just normal code equally well. So we believe that the modern IoT, cloud and AI services and devices can be protected. And also that digital resilience requires digital trust. And digital, creating this resilience starts with the validated, trusted hardware elements that needs to be used also secure way. So when I'm talking about hardware, of course, we need to have part of the software that has to be validated. And very often what we have seen is that the services and solutions are typically customized based on the purposes and requirements of the system, or the device or the system itself. So Xiphera has developed this special IP core, what we call crypto module, which is actually offering the cryptographic functions on hardware level. This secure boot and hardware root of trust and confidential computing that I described earlier, they actually benefit from and configure the crypto module functionality for the specific purposes. So I hope this has been giving you a little bit of insight. What is, how do we see fortifying digital resilience and offering the digital trust on the hardware level? So thank you for your attention.
Thank you, Petri. That is a very wide topic, but you had a good insights on the important aspects of digital resiliency. And we have already many questions in the Q&A inbox, so we try to go through all of them, but if you still have a question, please just submit it into the Q&A inbox now. All right, let's go through the questions. So, what is the metric for digital resilience, and when we know and how we know that it's sufficient?
Thanks for the question. It is an excellent question, pointing out. I was afraid a little bit that somebody is asking that. So let me go on the way that simple answer that there's no single one metric that we can give for when we have been achieving a level of digital resilience. It is a little bit like human resilience against diseases or sickness and so on. So there are multiple things that are influencing on our resilience. It actually would be maybe easier to say counter examples. So you can always prove by the counter example in the mathematics that is it true or not. So in the sense that we know that you are not digitally resilient if you are not verifying your designs, if you are not using components securely, if you are not managing supply chains or the tools, and if you are not testing the systems and so on. So to achieve digital resilience is not a 0-1 decision, but we can fortify it different levels and different means. And we have those tools, but the security has to be designed in from the day one. So that was a good question. Unfortunately, I don't have a black and white answer for that, because I believe it's like human resilience. It's built from the good sleep, good life habits, like having good lunches and having exercises and social connections. All of those are needed, like in the social needs for the people, also for the digital resilience is needing digital social networks.
Yeah, well, that was a hard question. And for the next one, it's about terminology. So the terms cyber resiliency and digital resiliency are often mixed. How do the terms differ, or is there any difference?
Okay, yes, again, going for the definition, I would say that cyber resilience is that when we are looking digital domain operating, is it using the best practices, access control scheme, management schemes, and so on, that we have kind of named functionalities. So I would say that cyber resilience is inside of the digital resilience, is actually the target that we achieve cyber resilience with the digital resilience. So they are not exclusive, and they might be overlapping, but digital resilience also is kind of maybe building the awareness about the whole concept that we have. For example, do we have skills to use this? Do we have education that is giving awareness of how to use, how to increase the resilience on designs, on different perspectives? As I explained earlier, these systems are very complex. So there's not anymore maybe one person that can manage it from the bottom to the top of the system. So coming back to the question, I think digital resilience is wider scope, where cyber resilience is important part and actually one of the goals to achieve. So we need to achieve both to have digital resilience and digital the cyber resilience. Again, one more question. So no black and white answer here again.
All right. So you talked about secure boot quite in depth, but can you elaborate a little more? So what is included in the secure boot?
Yes, okay, of course. So that was kind of introducing the concept that what we need to. So when we want to secure the boot, so we need to be able to verify that nobody has been changing the binary. So when you are developing code, or if you are deploying the AI model, you have bits and binaries. So we need to make sure that the integrity is checked, and the integrity checks are to perform typically with the cryptographic hash functions like SHA-2, SHA-3. And then when we have been calculating the integrity so that we know that nobody has been changing the content, we have to be able to digitally give the digital signature that I am the author, or you are the author of this signature, that you have the private key and you offer me the public key. So we are using asymmetric encryptions to guarantee that we can know the authenticity of the binary. Typically, those are elliptic curve cryptography, or now when we are looking for the post-quantum cryptography, that is, for example, deleting. Later, we can also look for the LMS, XMSS, and Sphinx Plus, and so on. So we need asymmetric cryptography. And then if we need to actually encrypt the data, we could be using authenticated encryption like AES and color counter mode, and of course in 256 bits mode with the keys, so that it would be the post-quantum cryptography compliant. So those elements are kind of how we are using the cryptography to protect the binary, and then of course on the receiving part, who is actually then using the binary, it has to be having the similar capabilities to be able to verify or decrypt those. So this went already kind of bit level information there, but this is what happens under the hood on we are using cryptographic primitives on the hardware level.
All right. Yeah. Thank you. Now we got a great question about the CCE. So let's jump the topic. So you mentioned ARM trust zone. Why would you need so complicated CCE solution? You mentioned at least security concerns with. Is there any easier alternatives to CCE, like software implementations?
Okay, yeah, this is a good question. So actually, CCE is making things simpler because we clean out the threats that are or vulnerabilities that have been seen there. So actually, the CCE is an easier way to deploy secure enclaves that we can do computations. What I mean with that one is because we are synthesizing the CPU there, we can verify all the functions that are on the CPU. We can actually change the CPU functions. We can actually change the compilers doing that. So the kind of complexities are maybe there, but actually you can use the same tool chains more or less and deploy the code there that is we are actually eliminating the known vulnerabilities of these systems. Of course, if you are using multiple enclaves and you are doing things that they have to communicate from enclave to enclave, then we would be bringing this cryptographic boundary that is protecting this enclave so that these two enclaves could be discussing with each other, sharing the data. But that is always, again, one aspect of what we say that we need to have a configurability and we make it fit for the purpose itself. So I would not say that this is more complex. It's actually making life much easier. Your lifetime management of the software, lifetime validation of the environments and so on, everything goes much easier because you don't have to be worried about the vulnerabilities on the other systems. So in that sense, it's not more complex, it's just a different and it's quite secure. That has been the basis of the design.
Yes, thank you for the answer. And I think we have time for one more question. So, how do you integrate with the supply chain security? So, for example, can we utilize some remote attestation to ensure the integrity and identity of devices from manufacturing through delivery of devices and the runtime life cycle of devices?
A wonderful question. Yes. So this is exactly how the system should be built. So that we should be able to remote attestate different phases of the manufacturing, different functions of these elements. However, even if we have these technologies available at the moment, those are not used and deployed in the sense that they could be to build this resilience and digital trust to the core. That question is good from the multiple perspectives, because it can be the attestation and remote attestation could be done during the power up on the operational environment. Also, if we are using kind of validation chain on this manufacturing, we could attestate those chains to be intact and not tampered with. So, very good question. And yes, actually, we would like to see that kind of attestability to be enforced. It would be increasing the digital resilience and also digital trust.
All right. Thank you, Petri, for your answers, and most importantly, thank you for your wonderful questions. But it's time to end the webinar. So thank you for your time today, and thank you for joining us. Please stay tuned for our next webinar happening sometime next fall. And remember to check our websites and previous webinar recordings. And have a great summer. Bye-bye.